Hello and welcome to the channel. Please greet very old and still very popular geometric problem discussed at various channels. Here I decided to demonstrate several approaches to solving it as another evidence of integrity and consistency of mathematics and the whole world. Three equal squares are bonded to each other in a straight link. Three segments are drawn forming angles alpha, beta, and gamma. It is required to find the sum of these angles. Let's name the lower vertices A, B, C, D, and the corresponding upper vertices A', B', C', D'. The side length of a square can be taken as the unit of measurement, in which case the side of each square will have length 1. Few things can be noticed straight away. Thus, triangle CD'D is a right-angled triangle, and it is also isosceles, as both its sides CD and DD' have length 1. Therefore, either of its acute angles is 45 degrees. In particular, gamma is 45 degrees. So the task is actually about finding the sum alpha plus beta. Now consider triangle BD'C. Angle gamma is an exterior angle of this triangle. Therefore, it is greater than any non-adjacent angle of this triangle. In particular, angle beta is less than angle gamma. Next, we consider triangle AD'B, where beta is an exterior angle, while alpha is a non-adjacent interior angle. So we conclude that alpha is less than beta. Finally, alpha is a positive number. From the obtained inequality, it follows that both alpha and beta are positive and less than 45 degrees. Adding the last two inequalities gives alpha plus beta is more than 0 and less than 90 degrees. And we carry over the obtained results to the next page, discussing probably the shortest solution, which however requires some knowledge of trigonometry. From the right-angled triangle AD'D, it follows that the tangent of alpha is the ratio of the length of opposite side DD' to the length of adjacent side AD. The ratio is equal to 1/3. In a similar way, from the right-angled triangle BD'D, we find that the tangent of beta is equal to the ratio of the length of side DD' to the length of side BD. So we get half for the tangent of beta. What do you think should we do next? We apply the identity for the tangent of sum. Substitute the values of tangent of alpha and tangent of beta, and get 5/6 for both numerator and denominator. So the tangent of alpha plus beta is 1, and there is only one angle which is more than 0, less than 90 degrees, and has tangent equal to 1. This is the angle of 45 degrees, of course. Hence, alpha plus beta is 45 degrees, and since the value of gamma is also 45 degrees, the sum alpha plus beta plus gamma is equal to 90 degrees. This completes the trigonometric solution and facilitates the other solutions, as we already know the result. Next comes the purely geometric solution, which is my favorite one as it requires just basic geometric knowledge. Take point E, symmetric to point C' about line AD. This means the segment CE equals segment CC' and has length 1. Also, angle ACE equals angle ACC' and is therefore a right angle. Now we draw straight line segments from vertex E to vertices A and D' and consider three right-angled triangles. Triangle ED'C' with right angle C', triangle AEC with right angle C, and triangle BD'D with right angle D. These triangles have equal sides. Sides EC', AC, and BD have length 2. Sides C prime, D prime, CE, and DD prime have length 1. And you certainly know what will follow. Indeed, the triangles are equal due to right angle side-side rule, therefore they have equal hypotenuses. ED prime equals AE equals BD prime. Also, there are equal acute angles. Angle C prime ED prime equals angle CAE equals angle D prime BD. And since the angle D prime BD has value beta, the other two angles have same value. Let's mark them as beta for clarity. We see that angles alpha and beta are now near each other and together form angle D prime AE. So once we find the value of angle D prime AE, the problem is solved. Can you figure out a way to do that? Let's bring back triangle AEC. We know that interior angles of any triangle sum up to 180 degrees. For a right-angled triangle like triangle AEC in our case, one angle is 90 degrees, while the remaining 90 degrees is the sum of acute angles values. One of the acute angles has value beta, and let delta be the value of another acute angle, angle AEC. So we can write that beta plus delta is 90 degrees. But there is another angle equal to beta, angle CED prime, and together with delta they form angle AED prime. Therefore, the value of angle AED prime equals beta plus delta, which is 90 degrees. In other words, angle AED prime is a right angle. And this is your last chance to complete the solution. Consider triangle AD'E. It is a right-angled triangle with right angle E. Moreover, as it was found before, triangle AD'E has equal sides, ED' and AE. Therefore, triangle AD'E is isosceles right-angled triangle. So its acute angles are equal to each other and sum up to 90 degrees. Consequently, each acute angle of triangle AD'E is 45 degrees. In particular, angle D'AE is 45 degrees, whose value is alpha plus beta. Hence, alpha plus beta is 45 degrees, and adding 45 degrees for gamma, we finally get alpha plus beta plus gamma equals 90 degrees. Next comes vector-based solution. We set up Cartesian coordinate system with origin at point A, x-axis along AD, y-axis along AA'. Again, we take point E symmetric to point C' about line AD and draw straight line segment AE. From the previous page, we know that angle DAE equals beta. However, this time we are supposed to use vectors. Here they are. Vector A corresponding to directrix segment AD' and vector B corresponding to directrix segment AE. Let's write the coordinates of the vectors. For vector A, x-coordinate is 3, y-coordinate is 1. For vector B, x-coordinate is 2, y-coordinate is -1. The angle between vectors A and B is alpha plus beta. And a chance for you to continue. Consider what is called dot product or scalar product. It is defined as product of the modules times cosine of angle between the vectors. In our case, angle between the vectors is alpha plus beta. So we find that cosine of alpha plus beta is the ratio of dot product to the product of modules. Module of a vector is the square root of sum of squares of its coordinates. Therefore, the module of vector A is square root of xa squared plus ya squared. And after substituting the values of xa and ya, we find that module of A is square root of 10. In the similar way, module of vector B equals square root of xb squared plus yb squared, and substituting the values of xb and yb gives square root of 5. For the dot product, we use well-known formula xa times xb plus ya times yb. Substitute the value of coordinates and get 5. Now we are ready to use the formula for cosine of alpha plus beta. Plug in the values for dot product and the modules. Number 5 can be represented as square root of 5 squared, while square root of 10 is square root of 5 times square root of 2. Then square root of 5 squared is cancelled out, and we are left with 1 over square root of 2 or square root of 2 over 2. We know that cosine of 45 degrees is square root of 2 over 2. And since alpha plus beta is positive and less than 90 degrees, no other value fits in. So we conclude that alpha and beta sum up to 45 degrees. Hence, the sum of alpha, beta and gamma is 90 degrees. And we move on to the solution based on complex numbers. Before getting to the actual task, let's recall basic properties of complex numbers. Any complex number z can be written in the form a plus bi, where a and b are real numbers, named real and imaginary part of z respectively. I is a symbol named imaginary unit. While operating complex numbers, we can replace I squared with negative 1. There is a one-to-one correspondence between complex numbers and points of a complex plane, so that real part is x-coordinate of a point, while the imaginary part is y-coordinate of the point. For that reason, x-axis of a complex plane is named real axis, while y-axis is named imaginary axis. Every complex number has a modulus. Also, a non-zero complex number has an argument. To find modulus and argument, we draw a so-called radius vector from the origin to the point representing the number. So, the modulus of the number is the modulus or length of the vector, while argument is the angle between the vector and positive direction of real axis. When multiplying two complex numbers, the module of the product is the product of modules, while the argument of the product is the sum of arguments. Since the argument is not uniquely defined, it is also considered principal argument, for which capital A is used. Principal argument is an argument which is more than negative pi and no more than pi, or more than negative 180 degrees and no more than 180 degrees. If real part of the number is positive, the principal argument is arctangent of the ratio imaginary part to real part. Now, after a 2-minute diversion, it's time to clear the page and get back to the problem. We convert our plane to a complex plane by taking point A as the origin, AD as the real axis, AA' as the imaginary axis. Let Z1 be the complex number corresponding to point D'. For point D', x-coordinate is 3, y-coordinate is 1. Therefore, z1 equals 3 plus 1i, or just 3 plus I. The corresponding radius vector is AD prime, therefore angle alpha is the argument of z1. Now let z2 be the complex number corresponding to point C prime. Coordinates of point C prime: x equals 2, y equals 1. Therefore, z2 equals 2 plus I. To find the argument of z2, we draw radius vector AC1 and get equal triangles, from which it follows that the argument of z2 is beta. What should we do next? Of course, we take product z1 times z2. Name it z. We know that argument of z is the sum of arguments of z1 and z2, that is alpha plus beta. Moreover, alpha plus beta is positive and less than 90 degrees, which makes it suitable for the principal argument. So we can write that alpha plus beta is the principal argument of z. Let's find the value of z. So we write that z equals z1 times z2, substitute the values of z1 and z2, and distribute. Then we replace I squared with -1 and merge common terms. The result is 5 plus 5i. Since the real part of z is positive, the principal argument of z is arctan of imaginary part over the real part. But both imaginary and real part of z are equal to 5. So we get arctan of 1, which is 45 degrees. However, the principal argument of z is alpha plus beta. Therefore, alpha plus beta is 45 degrees, and alpha plus beta plus gamma is 90 degrees. The only remaining phrase of this video. This is the end.